Recording. Okay. So welcome everyone. This is Bristech 17 and it's still online. We're seeing hopefully the end of the pandemic. We might be coming back to in-person events soon. Let's hope that happens. But for now, we are online and good evening everybody. For those of you who are new to Bristech, we started as a meetup. We spawned a conference in 2015 in Bristol. We did an MLOps event last year, and then we've taken a pause for obvious reasons. But the meetups have been still every month throughout the pandemic. Tonight, I am really pleased to welcome Ritchie Vink, who's going to be talking to us about polars, a DataFrame library, and we will have a Q&A after the talk, which will be, what, 20, 30 minutes. And then we'll vamp to the panel, and then we'll introduce another couple of people who have kindly joined us at quite short notice. So thanks for that, Joris and Joris. So the timings for tonight, roughly 30 minutes of presentation. We'll have a Q&A. Do put your Q&A into the chat, and then I'll ask you to unmute it at the end. And after the questions have dried up, we'll go straight into the panel. We hopefully close in about an hour. We'll see how we go. If we do run over a little bit, then do forgive me. Sometimes the chat is worth it. And do introduce yourselves via the chat window. Very interested to see who's here, what your backgrounds are, what you're interested in. So please do use that chat window for that. Everyone is muted. Please do unmute yourself if you want to ask a question. So over to Ritchie. Please do take it away.
Hi, thank you, Nick. Let me see, share screen. Is my screen visible?
Yep.
Okay, cool. What's the idea? If there's any question in the chat, you interrupt me. That's fine. If we can do this, or do we save it for the Q&A?
If it's okay, should we just save it for the Q&A at the end, and then you don't interrupt
your
flow? Yeah.
Yeah, sure. Hi, welcome everybody. Thanks for being here. I'm gonna talk today about my my pet project, which has gotten out of hand slightly. This is called Polars, and Polars is a DataFrame library written in Arrow. Written in Rust, based on Apache Arrow. Today I'm going to talk a bit about what Polars is in a nutshell. We're going to talk about the claim I have in the title, blazingly fast data frames. I'm going to talk a bit about the difference with pandas, because pandas is sort of the standard in the Python landscape, and everybody knows pandas and expects things from pandas. And we're going to go through some code examples showing the expression language. Most will be, every code I will show will be in Python, but it's actually almost a one-on-one mapping to the code in Rust. So if you want to use Polars in Rust, especially the lazy, it's the expressions are the same. So the only difference is that you're using some syntax difference because you're using Rust. Yeah, but it maps pretty much one-to-one. The development of Polars is sponsored by my employee, Xomnia. We're a data science company, and we're hiring, so take a look. They love it. Yeah, so why Polars? Why another DataFrame library? Well, the first thing was clear. I started to love Rust as a language, and I wanted to have a project. And Rust did not have a DataFrame library at the moment. And I was really thrilled about the Arrow project, and I wanted to do something with that. So myself being a machine learning engineer or data engineer and interacting a lot with data frames, I was thinking, hey, maybe I can implement what I miss in Rust for some needs I had in a server. That's how it started. It didn't start with a very serious idea. I'm going to build a fully functional, complete DataFrame library, which it has become. So later I acquired some more reasons, some more goals, I would say. Another one is that Moore's law is ending, which means that the number of transistors on a chip don't exponentially grow anymore. This was the case, and what this meant in software development was don't put too much effort in making code faster. If you wait 2 years, it will be faster for free. So there was sort of a free lunch in software development. This free lunch is over, and single-threaded performance isn't improving anymore. Or not much anymore. So what happens is that on the chip, they just scale parallelly. So they add more cores. But single-threaded code does not run multi-threaded. So the difference is that to get this extra performance, you need to rewrite your software. And the status quo, NumPy and Pandas are single-threaded and don't benefit from this hardware trend. There are other, no, I'm going to explain that later. And later, I also learned that there were a lot of knowledge in database development. So databases have been developing for, I believe, over 50 years. And there have been a lot of very cool optimizations, especially in query planning. And yeah, this knowledge is not really used much in machine learning pipelines yet, to what I see in the Python landscape. So I do see it in Spark, for instance, so more in the big data landscape, but less on a single machine. So I wanted to ingrain this technology from databases in the DataFrame library itself. And another one, which became a later goal, was that our data table really kicked our ass in the Python landscape. It was really super fast and was running circles around Python. So yeah, these are a few reasons to have yet another DataFrame library. Polars is based on Rust, and for people who don't know what Rust is a fairly new programming language which has performance similar to C and C++, but it's got a very original concept which is called I lost the term. The borrow checker. It's called differently, but Rust knows statically, so at compile time, who owns a piece of memory and how many aliasing occurs, or if multiple threads are writing to that same memory, then that code will not compile. And this means that there is a whole range of bugs which are not possible in Rust. No dangling pointers, no double writes, no threads writing to the same memory. And this is all checked statically. So this makes it, one, really easy to make performant code in with a lot less memory errors, and you're much more trustworthy of your program being correct. Especially when you want to write a parallel DataFrame library and concurrent DataFrame library, having Rust is really sort of a safe rails. But it does not come at a cost. So it does not come at the cost of control. You can still do everything you want with memory. So you can have the same control over memory as you have in C and C++. And this control is really what you need if you want to write the most performant software. So that's why Rust is a good foundation to write query engine in. The second core foundation is Arrow. This is also one of the reasons I started Polars, because I was really excited about the promises of Arrow, about this project. I think it's an immense undertaking, especially given the all the landscapes, all the languages they manifest themselves in. So what Arrow is different things. I would say mostly it's a standardization of a columnar memory store in memory. It's also, they also have compute kernels or compute on top of this Arrow standardized memory. They also have inter-process communication. And I think I have most, and they have I/O tools like reading Parquet or reading Feather, that kind of stuff. But what Arrow does by standardizing memory, it makes it very cheap to share memory between processes, because we all agree on how memory looks. We can use very optimal implementations. And this will save a lot of compute in serialization and deserialization. I believe 25% of compute in Spark is lost in serialization and deserialization. So going from Python to Scala, I don't know how they did it before Arrow, but it could be JSON, could be some other object notation. But this is very, very expensive. So Arrow aims to standardize this and save a lot of overhead and become the de facto standard of sharing data between processes, but also between computers, so over the network. And I think we will discuss later more about Arrow. So another thing that Polars has is lazy valuation. And this allows for an expression language, and it allows for query optimization. So lazy valuation gives me context to see what your intent is and how we might optimize this. So below we really have a sort of a trivial example of what the opposites could be. So a declarative style could be, let's say I want a cup of coffee, would be get me a cup of coffee, and then you say what you want. Procedural style could be explaining exactly step by step what to do. Take 5 steps of 75 centimeters, turn 90 degrees, take another 3 steps of 75 centimeters, and then I know mentally you're at the coffee corner. You need to rotate 45 degrees, lift your hand, pour me the coffee, etc. So you can write this code, and at the moment of writing this code, it makes total sense. But when you read this 2 years later and you haven't put comments then there, you're thinking, what were we doing again? So that's one downside of procedural coding. Another downside is that you as a programmer, you have exactly defined how to do it. This offers me as a library writer no possibility for optimization anymore. You as a programmer have complete control, but it may be because you're not into that, that you're not making optimal decisions. It can be because your query is getting more and more complex. It can be because you're not that into query optimizing. So by keeping things declarative, it allows the library writer doing optimizations. And it also is more clear. You can keep things more like English. Yeah, memory. Polars has got copy on write semantics. This makes it really easy to write pure functions. Pure functions are functions that do not change the input. It's a concept from functional programming. Functional programming hates modifying state, and with a pure function, you don't modify the input, you just return something new. But this can be very expensive. So if you would do this in pandas, and you want to add something to the data frame, but you don't want to modify the original data frame, you need to copy it to have for your pure function, and that would be expensive. So if you want to do that, that's a choice for the programmer. But writing a pure function is not always easy if your data type is large. Well, it is easy. It's not easy to do it cheaply. But in polars, all the arrays are reference counted, which means cloning data is free. Mutating single elements is expensive, but cloning data is free. Yeah, and as a result, you don't have the no setting with copy warning. If you know what it is, you're happy with it, about it. If you don't know what this warning is, never mind. So a difference between pandas is if you do a copy in pandas, you just actually copy the data. So there will be a new block of memory allocated, and the data will be copied. So if you do a copy 3 times, you end up with 15 megabytes of data. If your original data block was 5 megabytes. In polars, you have this memory block is wrapped in a reference counter, and this is similar to reference count, how Python objects are reference counted. There's a reference counter which determines how many points reference this, and if this reference counter is 0, then this object may be deleted. And same accounts for arrow memory. Polar's memory is arrow memory, and that's copy on write. So if we copy a block of memory, all we do is incrementing a reference count, and the memory increases very small, a couple of bytes. The downside of this is that if we want to mutate a single element in an array, we need to copy this whole array, right? So that's expensive. But turns out, overall, you win much more than you lose. Yeah, this is another example. Polar uses arrow memory, which is very tightly packed. And this causes a lot less indirection. It's very cache efficient. So it leads to very little cache misses, and cache misses are sort of the source of slow programs. If you go through data predictable, your code often is very fast. And also less memory fragmentation. So let me explain a bit how this works. So if I zoom in, is this clear? This graph? Yeah. Here's it's not entirely correct, I think. So what I want to show here is a pandas memory layout for a Python box string. So pandas use NumPy, and NumPy doesn't have string data, so not a string representation. So what pandas has done is they put Python objects into a NumPy array. So if you have a Python object, so this array is the array. So we have three strings, bar, ham, and foo, and they all point to a different point in memory. And so every pointer is an indirection, and you need to go to another point in memory, which is a cache miss, which will take a lot of time. So you have an indirection of 2, maybe 3. I think the Python C string is also somewhere else, so maybe you have a double indirection. I'm not really sure about this one. But yeah, reading this data is super slow. Another thing is you also have more memory fragmentation because you do a lot of small heap allocations. These blocks in between cannot be used for a large block. And there's also, this is not shown in the visualization, but you also have some tiny overhead of a byte per Python object, a byte for the C string because it's zero-ended. So per string, you also have a few bytes overhead, which may add up if you have a lot of small strings, which is not uncommon, I think, in DataFrame or in a common store. And in Arrow, this data is very tightly packed. So foo, bar, ham are all on a single memory block. And how do we know where the string starts and where the string ends? Well, that's done with offset. So we know the first starts at index 0 and ends at index 2, and the second starts at index 5 and ends at index 8, and the last one is the rest. And another thing that Arrow has is a thing called validity bits, which is bits, not bytes, but a bit indicating if a data point is valid. So if it's 0, it's a null. It's missing data. If if the bit is positive, then it's valid data. Yeah, and this is very wordy in pandas because they use NumPy, and NumPy doesn't have missing data. So they needed to hack the num, the floating point num for this. So this is a very interesting way. I like this very much about Arrow. It also opens door for pretty cool optimizations, which I don't go into in this talk, but maybe we can go into them in the discussion afterwards. But yeah, you can do cool things with this validity bitmap. So all in all, Polars has become faster than I would have dreamt, actually. It has. So what you see here are is a benchmark done by HTO AI. They do a benchmark of different DataFrame libraries, but also different databases and query engines. And Polars is one of the best performing query engines in this benchmark, and I think out there. So this is the join algorithm, which is twice as fast as data table, and I don't know, n faster than that of pandas. And this is the group by on advanced questions, which is like 20 times pandas, and this is on more easy questions of on a group by. Take a look at the complete data benchmark to see all the individual questions if you're interested. But yeah, so Polars is really fast. It's doing very well, and this is a pretty round benchmark, so you cannot hack one question because it will hurt another one. So they set it up pretty well. Yeah, I want to go a bit into the differences between pandas. One obvious one is performance and memory usage. This is due to using Arrow, due to writing everything in Rust, putting a lot of effort in optimizing cache efficient data access. And this leads to a 5 to 20 times runtime improvement. These are the improvements from the database benchmark. And memory requirements is a bit harder to test. I believe the pandas needs about 5 to 10 times dataset size. This number I got from a presentations a core developer of pandas gave themselves. And I believe for Polars you need 2 to 4 or 5 times. I think mostly 3 or 2. But yeah, it uses less memory, and I think this is one because copy on write semantics, and also by using pandas memory. By using Arrow memory and keeping everything tightly packed. Yeah. So this is in the design. Polars or Arrow really, I must credit Arrow for this. Arrow really has got first-class data types for databases and query languages. They really thought of what are the data types you need in a query language, how to deal with missing data, and due to this, you don't have this strange thing. So here we create a pandas data frame with integers, and we add a missing data on none. And if you look at the D type, you end up with a this fails because you end up with a float. So pandas schemas can change by the data you've got in it. So if this would be a valid integer, your schema would be different. You would have an integer. I think schemas may change due to operations, but I don't think they may change due to the data you've got in them. Another thing, this was a design choice for myself, is that Polars doesn't have indexes. I don't know if this is true, but it's sort of my subjective gut feeling. And one, code is read more often than written. And with pandas, I found the indexes always a bit confusing. I always saw a reset index multiple times, and always, okay, why do we reset this index? What is the semantics of this operation? You need to know what's the data behind it, or what does this index mean? It's often not really clear when you read a snippet. And I claim, I don't know if this is true, but I think the usage of indexes in the wild, how they are used in the wild, costs more compute than what they should say. I see a lot of reset index, and I don't even know what the thing is internally, if it's a hash map or a binary tree. But yeah, you need to compute that thing every time you reset an index, which is expensive. So I dropped them. And this also makes indexing predictable, because an index in pandas can be at least an integer and a string, and maybe it can be even more, I don't know. I think it can be more. But because it can be more, you need iloc and lock, because it's not really clear what you want to access. If you don't have indexes, indexing becomes predictable. We use the same semantics as NumPy. And if you put a string in there, we always know you want a column. Yeah. But indexing is not really the most, let me see how the time is. Oh. Indexing is not the, has it been 30 minutes already? Yeah, oh, okay. Shall we give it another 10? Is it okay?
Yeah, go for it.
Okay. Okay, I must speed it up a bit. So let's go into the expressions. Polars has a thing called expressions, which are functions over a series, which maps to a series. And they are very composable expression language. And you can combine them however you want. And this reduces the need for custom Python functions. If you run Python, you run Python bytecode, and this is always slow. And because because an expression takes a series and returns a series, you can combine them indefinitely. So let's go over to some examples. Here we create a data frame with some integer data, some string data, fruits, more integer data, some cars, and a column we don't use. And first, we're going to go over the selection context. So you can use expressions in different contexts. The first context is the selection context, which takes a data frame, and you can select any value from the data frame. And the data flowing through the expressions are columns in that data frame. And every expression you write is evaluated in parallel. So let's get an example. Here we write an expression all, which means get all columns. And here we write an expression all, and then we reverse the columns, and then we add a suffix dot reverse or underscore reverse. So what you end up with is first all the columns are selected, and then all the columns are selected, but the values are reversed. So here it's 1 to 5, and here it's 5 to 1. And this is done for all the columns. And you can use a lot of, you don't need to know the schema of the data frame. You can use things like select everything except this one, or use regexes, which you can use to select every column by name with a regex value. I'm going to speed up a bit, so if this is clear just now. We can also do aggregation, so we can select a column and we can compute the mean and save it as a underscore mean. And this would produce a single value, but such a single value we can just expand. We broadcast it to the size of the data frame. But we can also, before we do an aggregation, we can filter on a predicate. And so this is sort of like a super describe in pandas, which you can combine different kinds of statistics you'd like to have, but also based on different predicates. So there's no need to create temporary data frames by first writing a filter. You can do the filter inline, sort of. Yeah, I'm going to skip this one due to the time. If we want to combine column to a predicate, we have a when, then, otherwise. This is sort of a functional way of, if this is true, then I want column B, otherwise I want this. Also going to skim through this a bit. We can combine these things. Yeah, this is not really visible. So this is another thing. This is how you write neat pandas code. You pipe functions, right? So you have a function. What I often see in the wild is that people clone here because they want this whole pipeline to be pure, to not have the input data frame changed by the pipeline. So this clone is pretty expensive because you'll clone the whole data. And because Polars is copy on write semantics, you don't need to do this. And a similar function like this, where you assign column A by taking column B and adding column C, in Polars you can just return an expression. So you return the expression column B plus column C is an alias, and we name this alias A. And then in a context, you decide to run this expression. And in such a select context, this is also a super easy way to parallelize all your code, right? So everything that's not dependent on a previous column is run in parallel. So you can stack 15 expressions here, which will all run in parallel. But if you need code, if you need earlier columns, yeah, then you need to add them earlier. What's a good idea, Nick? Shall I? We can also go to the Q&A, or shall I? I've got some more examples, but I think people can also.
Yeah, maybe a couple more examples, and then we can wrap up
and
have questions. Yeah.
Okay, cool. There's also a group by context, which has got this syntax. You take a data frame, you group by, and then you aggregate and you add a list of expressions. Here, the meaning of expressions change because the expressions don't as input don't have a column anymore, but the input of the expressions now, the functions in the expressions are the groups of this group by operation. And again, everything is evaluated in parallel. So to make this visible, let's do a group by on foods, and then we take the column cars. And here you see that the output of column cars is now a list, right, with the groups itself. So instead of a flat column, you now operate on groups, list of groups. But again, you can combine these things with filters or with sums of aggregations. So you can really make very complex group by operations without the need of any Python lambda, without the need of running any slow Python bytecode. This is all run in Rust and all in parallel and all super fast. Yeah, this is another example of how you can combine things. So first we reverse, then we do a rolling min, and then we square it, and then we take the sum. And I don't know if this is possible in Pandas without using a lambda, but I think this shows the flexibility of using the expressions. You can combine and combine and combine indefinitely. And in my opinion, this is super readable because it's very declarative. And then we have a last one. This is called window functions. The syntax of this is you take a column, then you use an aggregation expression, or you use multiple aggregation expressions. You can combine again these expressions. And then you define over which group you want to use this. So the window function is sort of a group by, but then in the selection context. So the result of the window function will always be the same size of the original data frame, which means you can do a group by over different columns, but also over different column names. So normally if you do a group by over fruits, and you want to do a group by over cars, you need to do 2 group bys separately. And with window functions, you can do them in a single select statement. So here we show, we select the column fruits, we select cars, then we compute the rank by the column fruits. Oh, the name is flawed. It should be ranked by fruits, but then you get the rank itself in a list because a rank is the order of the things. But you can also, the names are a bit flawed. This should be mean by cars, but you can also compute the mean. So here we compute the mean of every beetle from column A. I should have selected A, then it would be a bit more visible. Sorry about that. But you can also, this is a cool one, if you take a window function and if you flatten that afterwards, you can do things in a group. So what this does is it takes these two, 1, 2, and then it flattens them in the group apple. And here it takes these 3, 1, 2, 3, and then it flattens them in the group banana. For this to make a sensible result, you can only do this on a sorted column. Otherwise, the groups don't match with the. But yeah, I really like the window functions because you can do multiple group bys in a single select statement, and they are automatically rejoined to your original data frame. And yeah, so sorry for the hastiness on the end. This was my presentation on polars. There are some final words. If you can also use full lazy execution, and then you get additional benefits of more optimizations. You get predicate push down and filter push down. These are all pushed down to the files. So this means if you scan a CSV or a Parquet file, that you will need to go through a lot less data if you only select 2 columns and you do a filter and you filter out 70% of your rows. This will mean that your memory will stay 70% lower because we will do this in batches and we filter out all these rows you don't need. So your memory will if you have very high selectivity, your memory will be a lot less. And polars can be a possible backend for, because it's written in Rust, it can compile, for instance, to WebAssembly. So it could be, you could have a very fast DataFrame library in JavaScript in the browser. It could be integrated with anything that would bind with C. It's a backend for NuShell. It's a backend for Elixir, which is for Explorer, a DataFrame library in Elixir. Yeah, and probably it can be for many other stuff. I want to thank Jorge for he's also in the loop a lot with a lot of optimizations we do on Arrow, and yeah, Polars has got a lot of stuff to thank on Arrow. So I also want to thank his work in making the final product better. And thank you.
Great, thanks, Ritchie. Everyone, if you want to unmute and show your appreciation to Ritchie for the talk. Thanks, Ritchie. We have a dog barking and a parrot squawking, but not tonight, unfortunately. But that was incredibly interesting. Thanks for that, Ritchie. So if you want to stop sharing the screen, perhaps we'll just go to talking heads. And if there are any questions from people, feel free to put them in the chat. Oh, we've got one to Kev. Do you want to unmute yourself and ask your question?
Yeah, sure. So it was interesting that you've got it working on WASM or WebAssembly. I don't suppose you managed to get the SIMD operations working on WASM?
I think I need to defer this question to to you, Jorge. You know more about this?
I was about to switch to VS Code and check if I can compile WASM with a sim. But no, I don't know, actually. I haven't tried it.
Cool.
And I can comply with sim with WASM, but I never tried both of them. So we have to try that.
Well, you've got 20 minutes, George. When you sort of crack on with that, and we'll
Yeah, good question. I honestly don't know. I know stable, so the default features compile to WebAssembly. That's being tested, which is already pretty fast, but it's not it's not full throttle. No.
Cool. Thanks. I've got tons of.
Any other burning questions from people? If not, I guess we'll vamp straight into the panel and introduce two people to you. So Joris van den Bossche, do you want to just say hi so people can key into your voice and maybe give us a little bit about your background?
Yes, good evening. So I'm Joris, I'm based in Belgium. I'm working on Arrow as well, but mostly on the Python bindings, which are bindings for the C++ library, not the Rust library, but the C++ implementation. And I'm, in addition to that, so I'm working at Voltron Data. Yeah, we are a lot of people working on Arrow on the ecosystem. But in addition, I'm also a maintainer of pandas. That's my earlier open source background.
Okay, so you have some interesting angles on this from a pandas perspective, then possibly. And George Leitao, do you want to say hi and maybe we can key into your voice too?
Hi, good evening, everyone. Yeah, I'm George. I'm originally from Portugal, but I've been living in Copenhagen. Background in physics, but I've been working a lot with data engineering more recently, and I'm in the Arrow for about a year and a half now. And I've been working mostly in the Rust implementation of Arrow.
Great. Well, welcome both. And I was laughing there when you were saying about the warty missing data, Ritchie, because that's something that I have been bitten by with the casting to floats. But presumably, like when when looking at pandas, that's kind of maybe not that's a grumble, but it's not maybe a major motivating factor. You mentioned like the multi-core support. Presumably, that's a much bigger deal.
Yeah, well, to be honest, I didn't start Polars as out of gripes of pandas. I never thought of building a complete DataFrame library. It grew organically, so I needed something I was writing a REST API in Rust, and I needed to do some DataFrame logic, and I couldn't, and so that's how it started. And while you're at it, hey, how is pandas doing? How fast am I? Oh man, I cannot even keep up with pandas. And so your goals are you're constantly adding goals. And okay, then hey, finally I beat pandas in performance. Oh shit, R is much faster. And then, oh man, my API really sucks. How can I make this more ergonomically to use? And so it's constantly shifting goals. And
so what you're saying, while everyone else was homeschooling their kids, you were busy benchmarking against pandas.
Yeah, well, also busy with my kid. I've become a father in that time, but it was maybe a sort of a away from the diapers.
An escape, perhaps. Yeah.
Yeah. Yeah.
So what I was wondering, what sort of analogy you would give to DataFrame libraries in general. I think so. I'm coming from an object-oriented background, and obviously you have object relational mapping tools, which effectively an API for transactional databases. So in what sense is a DataFrame library an API for an analytical database or analytical queries?
I think it's exactly that. Actually, I think it's an API for analytical. Yeah, it's OLAP. So I don't know. You have OLTP and OLAP. I don't know where it stands for exactly, but it's analytical processing and transactional processing. And in one, you need to, for instance, your ORM. It's really rudimental that if you update your bookstore's cashier value in your Amazon web shop, that is how you call this thing? This you named it, the translation. Yeah, that this translation is correct. And I think in DataFrame library you use this much more to modify groom data from one input to another, and you work on not on a single row but on a whole columns. You want to aggregate these columns and ask questions about it. But I think the difference between an ORM and a DataFrame library is that an ORM still uses the database. It's sort of an abstraction on top of the database and uses that database architecture and implementation. An ORM just maps that object model to a SQL query. And the DataFrame library is more query engine by itself. It implements their own join algorithm and their own group by algorithm and their own aggregations.
Okay. So I guess that leads to perhaps a fair amount of confusion about what Apache Arrow is and the sort of some of the distinctions, because I guess it's doing quite a lot of different things. It's got a lot of different responsibilities. George, could you maybe help us out a bit with kind of what Apache Arrow actually is? How would you define it? Oh, sorry, George, you're on mute.
Well, Joris, can you help me here? So I would say it's the component is the format, so the in-memory format. So how we place things in memory, how do we outline things in memory. Then we have the interprocess, the format, so the way we communicate data between processes. So even how it's allocated in memory, then how do we move these places in the processes? And then we have, I would say that the other main component is the Arrow, the flight protocol, which I'm actually not so familiar. So maybe Joris can say much more about this than me. But I would say it's the three parts, right, Joris?
Yeah, I'm also not an expert on flight, but it's basically also moving data around, but if you go across networks. So indeed, like the core is the memory specification, and then you have moving data around, interprocess with the interprocess protocols, so the IPC formats, flight across networks, and actually more recently, you also have the C data interface where you can move data around within process, for example, between Python and Rust. So really having, for example, Python and Rust working on exactly the same data in memory. So indeed, that are the different like moving data around. And then like a third layer, I would say, is then more dependent on each implementation, because you have implementations of those specifications in many languages, and we already have spoken about Rust, Python, C++. Python is a binding for the C++ one, but you also have a Java implementation, a Go, JavaScript, MATLAB, R bindings for the C++, and I'm forgetting a few probably. And then, so in those implementations, there is some varying amount of that you actually have, compute kernels, like actual algorithm implementations. I think the two most active there are the Rust and C++ implementations, but that's much more dependent on each implementation.
Okay. But I mean, that's fairly ambitious for an open source project, is it not, to be covering so many languages? Was that was presumably one of the goals from the outset, because having supporting so many languages leads to ubiquity. Was that the thinking, or am I wrong?
Yeah, I think I wasn't there from the beginning, but it's certainly one of the goals to be able to cross those different ecosystems. And like early in the beginning, you had mostly the Java implementation and the C++ implementation that are coming from two worlds. Like you have the JVM based things and the C-based things, and are really two different ecosystems. And by having a shared memory model and implementations of both, it becomes much easier to move at least as a start, move data between those two ecosystems. And from there it grew, and and many other languages starting to see, okay, that's an interesting model. We want to have an implementation of that as well, and it has grown a lot over the last years.
So is it fair to say that the design of Arrow was very much inspired by pandas? Is that a fair comment?
I think it's inspired by different things. So of course, Wes McKinney was one of the people that originally did the first implementation of Arrow. He comes from his pandas background, so has a lot of, broad data experience, but he also did it together with people from other projects, from other Apache projects, from more database oriented people. And it was really bridging those different worlds and with input from those different worlds.
And pandas uses NumPy, so under the covers, not Arrow, as we're hearing. Is that the Achilles heel, do you think, of pandas, if it has an Achilles heel?
Not necessarily. It's also, it has served us very well. Of course, it has limitations, but pandas also has become very popular, in part thanks to that we had NumPy to use. Of course, there are quite some limitations that are difficult to solve with the current model. Many of those things are already mentioned. NumPy has no real missing data support. Parallelization is not built into the core. Limited data types. So there are certainly limitations, and that's where Arrow, much more focused on this DataFrame use case, can provide a lot of, looking from the pandas point of view, can provide a lot of room to improve on those aspects.
Is a key difference that Arrow is written in a lower level language? Is that fairly significant? George,
what was the question?
How significant is it that Arrow is actually written in a lower level language, and therefore you can have bindings for higher level languages? Is that sort of one of the keys?
Yeah. So I think it's fair to say that the fact that the Arrow specification is not bind to a specific language did help, because it made the specification, one of the requirements is that the specification can be implemented in multiple languages. I think that's had a significant impact in how easy it is to Julia implement the Arrow specification, and Rust implement the Arrow specification, and Java and Rust, because I mean, in the end, these are very different communities, and they also have very different goals, and the languages have different purposes. So the fact that all of them can implement Arrow made it quite significant. So I think that is probably the core idea, is that it is not specific to a language, it is a specification. It's just saying, well, if you want to describe an array of integers, well, just put the data like this in memory, and the validity, so the nulls and non-nulls, just put it like that. And then each implementation then will just pick up this specification and say, okay, so we'll have to agree with this, so we'll just start laying out the memory according to this format. Okay. And the benefit that we all share by doing that in the different languages is that if I want to move data from Rust to C++ and into Python, it's zero cost, right? So, and that is kind of the beauty of all of this, is that from Polars can just call a Arrow kernel if we want, and the cost of applying that kernel is zero. And that is very powerful, right, as it's in itself. And that is for example, one of the main challenges of in Spark, of using this in PySpark, when you want to use the UDFs, so the user-defined functions. One of the main challenges was that when you wanted to move from the Java, so from JVM to Python, to then apply an operation in Python, that was relatively expensive. And that's why they started to introduce some way of serializing. I think now they're using Arrow actually to do this serialization, but at the time that was a challenge, and that is what you gain with this CData interface that Joris was mentioning. That you just move; it's just essentially sharing a pointer to in memory. That makes it quite interesting.
And that's all made possible through the standardization, which is defined in the specification. Yeah. Okay.
Exactly.
But
because otherwise people would have to say, okay, so if I look at the data like this, like an integer is just a bunch of bytes, but then other persons will look at in the raw format on which you have the integer and then the string, and then the integer and then the string, then we have to do something with the data to align, right? Both implementations, both the one on which the integers are all together and the one on which the integers and the strings are separate. And that's the cost, that's the serialization cost that you typically see associated with converting data from Python to Arrow, or from Python to Java, or some other mechanism, any conversion.
But we're specifically talking here about in-memory data. So when it comes to data on disk, then there's going to be some kind of, for example, if you've got Parquet files or whatever, there's also going to be the loading from files which have been optimized for storage rather than for in-memory.
Yeah, exactly, and that is one of the main costs of moving data to memory. Even if you are in Parquet, is that you will have to do a version from what is serialized in the format, so in disk, and even if you look at it in bytes, you still have to deserialize it to the target format that you want to look at it. So, and that is not just through Arrow, right? If you want to move data from Parquet to Python, to pure Python, just to the list, the Python list, you still need to perform that deserialization, and often also the decompression. So you need to decompress the file, and then from the bytes, the decompressed bytes, you need to kind of interpret them into the format that you want, and that still has a cost. Arrow also has its own format. It's this IPC format that Joris was mentioning, and it is highly optimized for not having to do a lot of those deserializations from and to Arrow. So it's relatively back to back, like what you have it in memory in Arrow, you generally just map it to bytes in the file. But of course, that is not so optimized for storage, right? Because now you don't have the compression. Now with Feather 2, you have some compression, but still is not on the level of Parquet, for example, which is highly optimized for storage. But correct me, Joris, if you have a different opinion here. This is nice because
fully correct. Yeah, and it can give I mean, there is still a big difference in how Parquet is optimized for really compressing and to small data. So if you have a lot of, if you have lots of data and yeah, storage is I mean, size is important. Parquet is a much better choice than using just Arrow to disk. Also, if you have to get data over network, it can be a lot more, it can be actually faster by having less bytes to download and then deserialize it than having maybe more direct mapping to your data, but having to download more data because of that. So in those contexts, it can those more advanced compression can have a lot of value.
What we have been experimenting with the IPC format in Arrow is when we don't have compute. So this is in the Rust, in the Data Fusion, and in the Ballista. But what we've been doing is that when we need, so in Spark, when you don't have enough memory to fit your calculation, usually you spill it to disk. So you start writing memory, the data to disk and store it temporarily while you do other operations with the memory that you have available. And in the IPC format, in that context is interesting because the operation of writing and reading to and from disk is relatively fast. So you don't need the serialization cost. So, and this is the type of operations that you don't need to store the data for long. You're just storing it for some time so that you can do the other calculation and then you just load the rest of it. So.
Yeah, so for temporary storage, the Arrow format is ideal. Then, yeah, okay, I hear you loud and clear. So maybe coming back to Ritchie, to you, and to Polars, I was interested in perhaps how you approach the API differently from Pandas. I know that it has a Pandas-like API, but Ritchie, you were talking there about the lazy evaluation. Can you maybe expand on that a little bit?
Yeah, this is something that grew organically. I always wanted to create a lazy evaluated DataFrame library while I started this. But in the beginning, I thought it was a bit more verbose, and so PySpark is also lazy evaluated, but people who work in PySpark don't often find it that intuitive, or well, maybe it is intuitive, but the fact that people often hack away in a notebook and they want to see the results right away, and they want to see intermediate results. So I was sort of on the tension between having an eager API and a lazy API, and those two got split. And I first wrote two APIs, and I was also documenting both. And the more and more I wrote lazy, the more I saw, hey, these expressions really are powerful. And if I throw everything on a runtime, I can do stuff people can do stuff that I didn't expect them to do, because they can combine any expression. And man, that API service I could not make. All this is a combinatorial explosion, right? So I thought, okay, really, we must use this lazy API, but how am I going to make this easy or interactive to use? And then I thought, wait, why just not throw everything we do on the lazy computation engine? So if you just do anything now with expressions, you actually do .lazy.collect under the hood. So you do exactly the same as you do in PySpark. And with this, I think you can have both things. You can have the niceness of the eager execution of the immediate result, but still have also the nice things of having those expressions. And the cool thing also is that when you're done with your coding, you can just bang a .lazy in the beginning and a .collect at the end, and you have also projection pushdown and predicate pushdown. And so there's a union between those two APIs, and they're not split anymore. So yeah, it grew organically, but I'm really happy with the result on this.
So that means you can prototype using one API, but then you would it would lazy evaluate when you actually have finished prototyping and happy it works how you want it to work.
Indeed, indeed. So when you're done prototyping, start with a .lazy in the beginning and bang a .collect at the end, and you're good to go.
Yeah.
Yeah.
And in terms of in terms of other differences to pandas, you mentioned there, and you sort of the validity bit optimizations and some of the other optimizations that you've done. Do you want to just say a little bit on that now, or is there something else a little bit more, other things more interesting you'd like to say about the differences between polars and pandas?
Well, there were a lot of optimizations. So I think I've spent almost 4 months looking at how can I do hash tables, grouping, so the group by algorithm was really the hardest algorithm there is in terms of performance. And there are a lot of optimizations in there, and also a lot of time. And things are also counterintuitive. For instance, first I did an indication. Okay, I think my cardinality. So I have groups, and so you don't know how many groups you have when you have DataFrame or when you do a group by operation. But let's say you do an assumption of your cardinality, and you say you have 10. You assume you have 10 groups, and then you can make an assumption of how big your hash map has to be. But if you do this, if you pre-allocate your hash map, it actually often is a lot slower. And this one was really counterintuitive for me. It turns out that so it's cheaper to start with a super small hash map, and every time that the data doesn't fit in the hash map anymore, you just reallocate, grow bigger, and copy all this. And this is still cheaper than doing the assumption first. And that's because if you over allocate, if you think about what a hash map does, you hash a value and you get a random point in memory. This random point is a cache miss. It's always a cache miss because it goes somewhere around the memory. So if you over allocate your hash map, you have guaranteed cache misses. So and this is, for instance, this is a lot more expensive than reallocating often. This is one of the counterintuitive optimizations I found, but there are a lot. And so there are very large optimizations, but there are also marginal optimizations. But if you have a lot of marginal optimizations, they start to add up, of course. And well, the optimizations, I must say, they are both in polars and they are in Arrow. And I think it's sort of a 50-50 part or something like that. So Arrow does all the aggregations, for instance. But polars also has a lot of compute kernels. So there is really a 50-50 thing. But one thing I liked about one cool optimization I liked about the validity bitmaps was that you can read those bits. You can read them as a large integer. So you can just read them as a unsigned integer, for instance. And if this integer is the maximum value, you know that 64 bits are set, which means you can if you do a filter operation and this value is the maximum size, you can read all the 64 values. You don't need to compare them anymore. So this is one of the optimizations done in Arrow, which I found really cool, that you can, by reinterpreting those validity bits as an integer of a certain size, with in some cases you can blaze through these filter operations. And if you check the filter performance of Arrow versus a filter in NumPy, you really see that Arrow is a lot faster in the selectivity where, so for instance, if you filter nulls, I think nulls are often, most of the times, like 20% of your data or something. So the 50-50 case, that's the bad case, right? Because then you have a lot of branches, a lot of branch misses. So then this optimization doesn't work. But if 80% of your data is valid or null, then you can blaze through those filter operations. And you really see that this filter in Arrow is a lot faster than in NumPy. And I think this is due to such tricks. And there are tons of these really cool things, both in Polars and in Arrow. Yeah.
So, I'm wondering, does that mean, Joris, that Pandas 2 is going to maybe take inspiration from some of these optimizations and approaches? Is that potentially on the cards, Joris?
Maybe just first to say something about the difference between Pandas and the optimization Ritchie has been talking about. Personally, what I find very interesting about Polars and seeing what Ritchie is doing is more the API and not that much those optimizations. Of course, they are important and interesting as well. But in general, there are several DataFrame libraries and also in Python. And many of them, try to mimic Pandas or more closely than what Polars is doing. But seeing someone experiment with possible alternative and more powerful API is actually more interesting than someone mimicking exactly Pandas. I mean, you learn more from seeing what people experiment with. So I think that's certainly also on that level, it's certainly an inspiration for what could be possible, or what are possible improvements in API, in functions, in Pandas. Of course, we don't have at the moment, we don't have any expression system, so that makes it more difficult. Maybe it's something that we should add. Related to the optimizations, many of the optimizations that Ritchie was mentioning are also, for Pandas, it's the C++ implementation of Arrow. They also have many of those optimizations. So if it comes to those low-level optimizations, I don't think that it's up to Pandas to implement them themselves, but it comes to better leveraging Arrow under the hood. That is certainly, something we should do as Pandas. How this exactly will look like, that's very much open, and Pandas is a very big project with many people contributing it, but also many people using it. So it makes it a slower beast to evolve than something like a new library. But that's certainly one of the directions for Pandas, is to make more and more use of Arrow, so we can gradually benefit from those optimizations. There are already a few areas where Pandas currently uses Arrow. Most importantly, the I/O. So if you read Parquet files, obviously you're actually using Arrow. Also now, for example, for CSV files, you can use, it's not yet the default, but you can use the Arrow CSV reader, which then also is parallelized and faster than our own. For string data, we are starting to use optionally the Arrow implementation. And that was one of the examples that Ritchie gave. Currently in Pandas, we use Python objects for each string. So we have an array with pointers to each individual string, while in Arrow memory, the strings are packed together with much faster algorithms for that. So that's something that we are starting to integrate in Pandas as well. So there, but it goes a bit slower and more gradually.
Okay, understood. Sounds great. I just realized we've run over quite heinously. It is almost 1:15. And also we had a question from Taurine, which I didn't pick up on. So Taurine, are you still on? Do you want to ask your question? I do apologize for missing you earlier. Maybe he's not there. Anyway, okay. Sorry, Taurine, for that, if you're watching on replay. So any final thoughts from our panelists after what we've heard? Maybe do you want to maybe one closing or concluding remark from each of you, and then maybe we'll close. Ritchie, do you want to any
Oh,
final final words?
Oh, I've got the final word. Gosh. No, please take Polish for a spin and tell me how you like it.
Are you looking for
the feedback is always very welcome. I learned a lot of the API comes also from learning how people use it, because you're really in an ivory tower when you're thinking of things, and every day you're sort of surprised again by, oh wait, that's also something people want to do. So please use it and give feedback. And yeah, thanks for your attention.
And hopefully that could lead on into contributing as well, Ritchie?
Yeah. Oh yeah, that's another one. Yeah, if people want to contribute to a cool Rust project, I'd like more contributors. So yeah, feel welcome.
And George, any final remark from yourself?
Yeah, I just want to thank Ritchie for the open source contributions and all that work. It's quite impressive how much you dedicate to Polars, and it's a great library, and I think it has a very cool stuff and a lot of potential to change a bit the landscape of the data frames, both in the API, but also on the fact that we have a very strong statement about performance, about thread safety, and about security in general, and of course also to Nick for inviting, and Joris also for all the great work in the open source. It's a very well-known figure in the open source. It's great to have him here today. So thanks a lot.
Awesome, thanks, George. Joris, any final word from yourself?
I will leave it to what I just said before. It's very interesting to see, Polars, and in general, I think with all the different things that Arrow is enabling, and to see everything that's coming out of the Arrow ecosystem is very exciting to see. So yeah, and also thanks for the invite. So I'll leave it at that.
No worries. It's been a good night. So thanks, Ritchie. Thanks, George. Thanks, Joris. And thanks everyone for tuning in. All our videos are up on the website, so check out the Bristech YouTube channel. There's tons of good stuff up there. Next month, we have Kevin Coe from Prefect.io talking about data workflows using Prefect. I think that's similar to the Apache Airflow. And Prefect is also open source, so hopefully we have some more open source chat. So thanks very much to everybody, and have a good night, and we'll see you again. Bye-bye.